You can start.
Oh, okay. Hello, welcome back to another Mathcounts meeting. Today we're going to finish 2016 Nationals and then we're going to start 2015 Nationals. So, do we do this problem?
I don't think we did. Yeah, I don't think we did that problem.
All right. Two square tiles, each with sides of length 6 inches, are arranged so that one lies directly on top of the other. The top tile is then rotated counterclockwise about its center until one of the exposed corners of the bottom tile has height 1 inch as shown. What is the area of the shaded intersection of the two tiles? Express your answer as a decimal to the nearest tenth. All right. Oh, what? All right. So this figure is symmetrical, right? Which means that every little side like this is going to be 1 inch. So like this side, this side and this side, all of those are 1 inches. So let me just draw the figure at the bottom here. So we know this side is 1 inch. And from symmetry, we know that this side is 1 inch. It doesn't look my figure isn't perfect here, but if you look on the you can just look on here, yeah. And then so this is also 1 inch. Both these sides are 1 inch. And then we can say some side is x. We can let this side be x. And these are all right angles, right? Because they're all the corners of the square. And also from symmetry, this is x, and from the symmetry, this is x. And so we can just apply the Pythagorean theorem here, right? To get the lengths of the hypotenuses. So these would just be 1 plus x squared rooted. And so we know the side length of the square is 6, right? And we have 1 here, we have that there, and we have x here, right? So that means we can set up an equation where all this equals 6. And then we can subtract 1 on both sides to get that equals 5. Now, how you want to solve equations like these is you want to get rid of the radical, right? So we want to move everything that's not under a radical to one side. So then we can square it, and we're not going to keep the radical. If we square it here, we're going to get a radical term when we multiply those two together. So now we can square both sides to get rid of the radical. You can cancel out the x squares. That's nice. And then we have negative 24 equals negative 10x. So then x is going to equal 24 over 10. Then you can divide 2 from both sides to get 12 fifths. All right, so we just solve for x 12 fifths. And we want to know what is the area of the shaded intersection of the two tiles, and we want to express our answer as a decimal to the nearest tenth. So what we can do is we can find the areas of these small triangles, multiply by 4, and subtract it from 36, right? Because that's the area of the whole square. So the area of our triangle here is going to be 1 times x, which we said was 12 fifths. And I'm going to multiply this by 4. Oh, by 1/2 actually, yeah. And we're going to multiply this by 4, and we're going to subtract it from 36. So this is just going to be 2 times 12 fifths is 24 fifths. So then we just have 36 minus 24 fifths. And this is pretty easy to solve by hand, but you also have a calculator on the team, so we can just use that. All right, so if you put it into the calculator, you get that this equals 31.2. And then we can look at the answers. Yep, that's our answer, 31.2. Honestly, this problem was pretty easy. Just use the symmetry there. All right. The display on a calculator is broken so that when the calculator shows a number in decimal form, The tenths and hundredths digits of the number are never visible. Shauna enters a positive integer n in the calculator and presses a button that gives the reciprocal of the integer in decimal form. The 9 digits following the missing digits in the display are all threes. What is the sum of the possible values of n? All right, so our calculator, we can't see the tenths or hundredths digit of the number, so those are empty, or we don't know what they are. And then after this, we have all threes. And so what happened was she took the reciprocal of some positive integer n, right? And this equals that 0 point something something and all threes. And we want to find all the possible values of n. Okay, so this is an interesting repeating decimal problem. So we can use my my trick, my technique thing with repeating decimals. It's like let's say, I don't know, you had 0 0.54 or okay, 0 0.5893333 and so on. And then what would this be in fraction form? Well, my trick is to take numbers all the way. So okay, so this is the repeating part, right? So okay, so put it in the repeating notation, and then take all of these numbers, but don't have the repeating part, and then and put it as an integer, and then subtract the non-repeating part. The non-repeating part is 589, and then put it over the number of nines for how many repeating digits you have, and the number of zeros for how many non-repeating digits you have. So we have 3 non-repeating digits and we have 1 repeating digit. So our fraction should be this. Let me just check on the calculator. Yeah. So if you put this into your calculator, you see that you get 0.589333 and so on. So we can apply that here. We can say that this digit is x and this digit is y. So then we can use the fraction thing, and we can say that this will be 100x plus 10y plus 3. And then, so we're just taking this first part right here, like right there, and then we're going to subtract the non-repeating part, right? So that's going to be minus 10x minus y. And then we're going to put it over 900 because we have 1 repeating digit and we have 2 non-repeating digits. And this will also work if x or y or both are 0. So if both of them are 0, then we have like 3 over 900, and you can see that will work. If we put it in, we get 0 0.00 and then 3s. So it does work as x and y are 0. Okay, so now we can simplify this. We have 90x plus 9y plus 3 is, or over 900 is going to be 1 over n. And then we can divide by 3, right? So then we have 30x plus 3y plus 1 over 300 will equal 1 over n. All right. Now we just need to find the possible values of n. How this is going to work is we need so we can take the reciprocal of both sides here, right? So then we get n equals 300 over 30x plus 3y plus 1. And n has to be an integer, right? So then what we have to do is we have to make this a factor of 300 while keeping x and y digits. So x and y will have to be in the set of digits, which is the integers from 0 all the way to 9. All right. All right. So what can we do here? We can list out the factors of 300 and then try to find x and y's for those. What do you think, Bill? Do you think that's the best way?
Um, yeah, you could probably do that. Yeah, that's probably. I mean, what else are you gonna do? Uh,
Sure,
yeah.
sure, we can do it like that. Okay, so let's look at the factors of 300. So we can take out a 100 and a 3, and this is just 10 and 10, and that's just 2, 5, and 2, 5. So not that many factors. So we could just list all of them out. Let's go ahead and do that. So so we have 2 squared, 3, and 5. Okay, so don't forget the 1. And then let's just I'm not gonna list them in increasing. That doesn't really matter, and I'm just gonna get them all out. So we're gonna have 2, 4, 6, 10, and then 12 and 20, right? So those are the ones with 2, and then we're gonna have 3. Oh, whoops, there should be a 5 squared there. So we're also gonna have what? Uh 2 and 5 squared, which is 50. 4 and 5 squared, which is 100. 2, 3, and 5, which is 30. And 4, 3, and 5, or uh, yeah, 4, 3, and 5, which is which is wait, oh yeah, 4, 3, and 5, which is 60. And then we have 4, 3, and 5 squared, which is 300. And then did I count 2, 3, and 5 squared? That's no, I didn't. That's 150. Okay. And then so those are all the ones with 2 and 4. And then let's look at just the ones without 2 and 4. So that will be 3, and we have 5 and 25. And then we have 15, 75. Um, and do we have anything else? Uh, I don't think so. I think I got all of them. Oh, with the we can also check with the number of factors formula. So the number of factors of 300 is going to be each of these exponents times each other when they're added to 1. So the total number of exponents will be 2 plus 1, which is 3, times 1 plus 1, which is 2, times 2 plus 1, which is 3. So we should have 18 factors here. So so we have 12 there, and yeah, we have 6 there. So that's 18. So we can check that we listed all of our factors here. Um, oh, okay, a little bit of a smarter way to do this might have been to check the mod of this first. Um, so like we have 30x plus 3y plus 1 equals something, right? And we need x and y to be integers. So whatever we have has to be 2 mod 3, right? Or sorry, not 2 mod 3. It has to be 1 mod 3, right? It has to be 1 mod 3. So that when we subtract the 1 here, it will be 0 mod 3, which means it's divisible by 3. And then, this is divisible by 3 as well, right? And those are integers, so we have to have this as 1 mod 3. So then we can cancel out all of our factors that don't have that, or sorry, that aren't 1 mod 3, and that will save us a lot of time, right? So let's go ahead and do that. So 2 won't work, 6 won't work, 12 won't work, 50 won't work. None of the ones with 3 won't work. So if we noticed this earlier, we wouldn't have to list out the factors with 3. So that was kind of my mistake. Um, All right. So it seems like we only have five to work with now. So that really helped us there. So now we can just check these. Five cases isn't too much. So let's just work with that. So in our one case, we will have this equals 0 or 10x will equal negative y, right? Yeah. Or I don't know. Yeah. Or 10x plus y equals 0. So this is impossible, right? Or only when x and y equals 0. And that's actually the case. Never mind. Yeah. So x and y both have to be non-negative integers, right? So if they're greater than 0, then you can't have anything to bring that down. So the only case that works here is when they're both 0. So we can list our cases that work there. So 0, 0. All right, now let's look at 4. So when we subtract 1 and divide by 3, we're going to have that 10x plus y will equal 1. And x has to be 0 in this case, right? If we have x to be anything or greater than 0, then that would be way too big, right? So x has to be 0 and y has to be 1. So we're going to have 0, 1 there. Then we have 10. So 10 will be 10x plus y equals 3. And again, with the x thing, y is just going to be 0, 3. And then 100. 100 is going to be that this equals 33. Whoops. And the only case that works here is 3 and 3, right? And for all of these, we can see that there's actually only one case for all of these, right? Because x kind of acts like, or basically, x has to be the tens digit and y has to be the units digit, right? So it's just going to be like that. And then 25, it's going to be 10x plus y equals 8, which means that it's just going to be 0, 8. All right. So those are all of our possible cases. Now we just need to find what n is. So now we just plug it into our formula, right? N equals 300 over this stuff. And so listing out the cases here was actually kind of a mistake. Like it kind of wastes time because there was a shortcut to finding n actually. So basically we could have noticed that all of these will have some case that works with x and y, right? Because once we minus 1 and divide by 3, it will just be the tens digit and the units digit for x and y, right? And so then we could just plug in these numbers into that, right? Because that is what we are setting these numbers equal to. So we really didn't have to find all these x and y stuff. We could have just plugged in all 5 numbers into there and then summed what they were. And then that would have saved us some time. But yeah. Okay, so let's do that. We have 1, so that's going to be 300. We have 10, that's going to be 30. We had 300, that's going to be 1. We have 25 and 4, so 25 is just going to be 3 times 4, which is 12. And then 4 is just going to be 75. Yep, and then we just need to sum this, and we have a calculator actually, but it's not that hard. Okay, so then this is 418. That should be your answer. I'm missing one case. I think I might have made a mistake. So we're missing 2 here. Um, did you see where I went wrong, Bill?
Um,
If we had 150, it would work, but that's not a case. Oh, whoops. I see my mistake. I said we had 300, but we actually had 100. So I thought we had 300, so I had the 1, but we actually have 100 instead. So this should be 3, right? So then that would increase our thing by 2. So then it'd be 420. Okay, yeah. So uh don't make little mistakes like that. Like we did all of it correct, except we just missed that very small thing at the end, and that would have made us go that wrong. So yeah, be careful of that stuff. Yeah. So this problem was kind of long. Um, it's it's a decently hard problem, I would say. All right. Oh, this one. Oh gosh. Okay. In a grid of unit squares, the snake is a sequence of distinct unit squares beginning with the upper left corner and ending with the lower right corner, such that any two consecutive squares in the sequence share an edge, and no four squares in the sequence share a single vertex. Examples of a snake and non-snake are given for a 5 by 5 grid. How many different snakes are there in a 5 by 5 grid? Okay, so basically what this is saying is we start our snake starts at A, and then we move around the grid. And then when we move, the squares that we go to, well, we can't go to the same square twice, but also the squares that we go to, it can't form a square like this. They can't meet to one vertex. And then that would be not a snake. And we have to reach B. And that's all the restrictions that we have. All right. Um, so what I would start with is um, by saying that if we go right or down, they're both symmetrical, right? So then we can assume our first movement to be right, and then all the cases that we have coming from right, we can just double that, accounting for the down cases, and that works because both of them are symmetrical, right? So we can assume the first move to be right. And let me just make a grid here actually. That's a little bit off. All right. So we can say our first move is to the right, and then we need to remember to multiply our final answer by 2. So I'll big circle this times 2, so we won't forget it. Okay. So now what do we do? So um you can think about this for a while. One thing that I would notice is that let's say you're on the final or the fourth row. Yeah, let's say you're on the fourth row. Then where can you go? Um, so like you just came down and you're on the fourth row. Where can you go? When you go down from the fourth row, you can't ever turn left, right? Um, because if you turn left, so like when you come down, you have to like make some sort of barrier that blocks you to B, right? So if you go left, you can't get through that anymore. There's no possible way you can get through that, right? So so when you're on the fourth row, if you go down, then you have to go right. You can't go left at all, right? Um, so that's one thing helping us. It's saying that if we're on the fourth row and we go down, we have to go right. Okay. But on the fourth row, we don't have to just go down, right? We could also go right if we wanted to. Now, we can't go left, right? Because if we go left, we can't go here to go to B because we blocked that off, right? And we also can't go down, we can't go back down to go to B because that would form our square thing there, right? So if we're on the fourth row, we can only go down or we can go right. And if we go down again, we can only go right. Okay. Okay, so that's interesting, right? Um, so we can think about it like this now. If we're on this square, like if we reach the fourth row on this square, then we only have one more case. We just move down, right? If we reach the fourth row on this square, then we're gonna have two cases, right? We could go right or we could go down. So if we ever reach this square, um, we're gonna have two cases there, right? And then if we ever reach this square, we're gonna have three cases, right? So we can go there, there, or there. And then if we reach here, we're gonna have 8, and if we reach here, we're gonna have 10. Okay. So now we can think of it like, which fourth row square am I going to reach? And from that, calculate how many cases there are for that. So that helps us a little bit. Okay, but we have to be kind of careful there. So I said like each of these squares was one, two, one, or wait, what? Or sorry, this should be three cases, this should be four cases, and this should be five. Sorry if I said otherwise, yeah. Okay, but we have to be careful here. So it's like this square, if we reach this square, I said we had five cases, right? But that's not entirely true. If we reach this square from a position like that, we don't actually have five cases, right? Because we can't go right now because this would form a square. So in this case, we will only have one case going down. So basically here's the thing now. If we had like any squares to the right, we have to subtract some cases. But if we go to the square and we had no squares on the right of the third row, then we'll have all of those cases that we just said. Okay, so hopefully that makes sense. All right. So now what we can do is we can look at the first row now and have cases for every position going down. So we first look at this square going down and we list all of our cases. And then we look at this square going down and we look at all of our cases. And we just do that for all of them. And then if we do that for all of them, then we should account for all of the cases and we multiply that by 2 and we should get our answer. All right, so let's start with going down from this square or this column. Okay, so we go down. Now we can't go left, that would form a square. So we can go either down or right. Let me look at just the down case for now. All right, so if we go down, let's look at how many cases we're gonna have. So if we go left, we can only go here to the square, right? And then we have a right blockade right there. And so then we would only have one case for that square, right? So that's one. And then what happens if we go to the square? Well, we have no right blockades. So then all of this square's cases would be accounted for. So that means we would have four cases right there. And then we could also go right to that one. So that would have three cases. We could go right to this one. So that would have two cases. And we could go right all the way to this one, and that would have one case. And note that you can't ever like go back up and come back down, right? There just isn't enough space to do that. We can't come back up on this column because that would interfere with that. And if we come back up on this column, then we don't have enough space to come back down, right? So we don't ever have to look at the cases where we come back up. Just where we're going down. All right. So down to the right and sometimes left. Okay. So now let's look at if we go left, or sorry, if we go right here, right? So if we go right here, we can go down or more right. So I'll just look at down for this now. So if we go down, we have or okay. So let's say we go down again. So we can't go left. We have to go down or right. Okay. So let's say we go down. If we go down, we can't go left. So we have to go down or right, and there's nothing stopping that, right? So that will have three cases. And then okay. And then what happens if we go down somewhere else? So what happens if we go down here? Then, we can't go there, but we have no right blockade, so that would have two cases right there. And we can also go down there, so that would have one case right there. All right. So that accounts for if we go down on that column. All right. And then what happens if we go over here and then we go down? Well, if we go down here, we can't ever go left, so we have to just go down or go right, right? So okay, so if we go down, we're gonna have two cases here. There's no right thing stopping us. And if we go down, we can also go right down there. So that's one case. And then if we could just go right there, then our only case is just going straight down, right? So that's just one. Phew, okay. So that's all of our cases for that second column going down. So now we have to look at the other columns going down, and they should be a little bit better because the second column would have the most cases, right? All right. Okay, so now let's look at the third column going down. All right, so what happens if we go down from here? We could go down here, we can go down here, or we can go down here, right? Now, or we could go down here. Actually, yeah, we could turn left and we could go down there, right? Okay, so if we turn left and we go down here or here, there's going to be a right blockade there, right? So we can't, each of these would only have one case, which would be just going down and going all the way to the right, right? So that would be 1 plus 1. And then we could go here. Now, these three squares are going to have no right blockades, right? So those are just going to be their total number of cases. Okay, so that was if we went down from the square. But what if we go right? All right, well, if we go right, and let's say we go down, then we could go left to any of these, or actually we can. If we go left to any one of these, then if we come back here, we're gonna form a square, right? So we can't go left here. So that means we have to go just down here or right here, which is just two cases, right? And what happens if we go right here? Then there's just one case. All right. So now what happens if we go all the way right and then we go down? Well, then that's one more case. All right. So that was the third column going down. Okay. So what happens if we go down on the fourth column? Well, if we go down on the fourth column, we can go right or down. Let's just look at if we go down for now. So if we go down, we could go left and come down to any one of these fourth row squares, right? And we could also come to the square, right? Or these squares. So if we go left into any of these, we're gonna have right blockades, right? So each of these three squares are just gonna have one. Now if we go down to these two squares, they're gonna be their totals, right? Because we have no right blockades. So that's gonna be 2 plus 1. So that accounts for if we go down here. So we need to look at what happens if we go right. If we go right, we can't go left anymore, right? Because we can't go left on this road because there's a blockade there. And if we go left there, we don't have room to come back. So our only case is just going straight down. So that's just one. All right. So that was all of the fourth column. Now we just have to look at the last column. Now on the last column, we have to go down and we have to go down again. And then what can we do here? We could go left to any of these squares or go down to the square, right? And all of these squares are going to have right blockades. So all of them are going to be 1, right? So then we're just going to have 5 ones. And then there's nothing else to do here, right? All right, so if we counted correctly, this should be all of our cases. So let's just sum that up. So this is going to be 10. That's going to be 6. That's going to be 4. And then if we pair this one with like this stuff, then we're just gonna have 8 there. And then we're gonna have 5 there. And then we're gonna have 6 and 4, that's 10, and then 12. All right. And then what's this? Well, that's 10, that's 20, that's 28, that's um 32, that's 37, and then that's 49. All right, and is this our answer? Oh, sorry, is this our answer? No, because remember, we had to multiply it by 2 at the end, right? To account for the down cases. So you have to remember that. So yeah, we multiply by 2, and then we have 98 as our final answer. Oh, whoops. The answer is 90? Uh-oh. Uh, Bill, do you have any idea where it went wrong?
The way you did it, it's going to be very easy to miscount. So
Uh, I think I miscounted this,
it will be
actually.
very because you're
Uh,
basically counting like just going around counting every solution. So it will be fairly easy to miscount. So
yeah. Yeah, you have to be really careful here. Let's just count my thing again. I think I counted it wrong. Okay. Well, let's just count it more systematically. So, so this is gonna be 11, and then this is gonna be 6 and 4, right? So that's 10. This is gonna be 6 and 2, so that's 8, and that's gonna be 4. And then this is gonna be 6, and without 1 is 7, and that's gonna be 5, and that's it, right? All right. And then we have 21 here, we have 12 here, so that's just gonna be 32. No, it's gonna be 33. Yep. And then we have 12 there, and then we have 45. Oh, okay, yeah. I just counted our countings wrong actually. So now if we multiply 45 by 2, then we have 90, and this is actually our answer. But yeah, the doing this is very easy to make mistakes, very easy to um overcount or not count a case. And yeah. But um I don't know. There isn't like that much of a better way to do this, I don't think. Um, what do you think, Bill?
um, there really isn't like that systematic way. I wouldn't think so. Unless you could try like counting the cases that is not a snake.
Oh yeah, but that's also like really
That
hard.
will be yeah, that will prove to be interesting, I would say.
No, yeah, I think that would be even harder actually. Yeah, but there really isn't like a good way to do this. Um, so this was the best way I can think of to do it. Um, but yeah, it is really easy to make mistakes here, and it takes quite a while. So if I were on this problem, I would probably save this to do at the end if I have time at the end. Because it's fairly easy to make mistakes here, and it's going to take a fairly long time. So I would save it to the end. Anything else you want to say, Bill?
Um, yeah, I mean what he said. This is a tedious problem. So
Ooh, we can check how many people got it
yeah, we
right.
can check how many people got this right. We have the score distributions.
4. Nice. Yeah, it was really hard. The second hardest team question. All right. Let's move on now. Two squares lie inside right triangle ABC so that each square has one side on leg AB. One side of the smaller square lies on a side of the larger square, and the larger square has a leg on BC. Each square has a vertex and a hypotenuse AC. The area of the associated triangle is 9 over 289 of the area of triangle ABC. What is the ratio of the area of the larger square to the area of triangle ABC? Express your answer as a common fraction. So basically, we have this figure here. We have two squares inside the triangle. We want to find the ratio of the area of the larger square, the square, to the area of the triangle, given that the shaded area is 9 over 289 of the larger triangle. Oh, whoops. How do I get rid of that? What the heck? Okay. All right. So where can we start? We can start by noticing that we have a lot of similar triangles here, right? So ABC is a right triangle, and okay, let me just draw the figure. Okay, so we know ABC is a right triangle, but because these are right angles, then these triangles are also going to have right angles, right? And we can see that this angle is shared with ABC, right? Of this smaller triangle. So then this smaller triangle and ABC will have two angles or two angles equal. So then by AA similarity, those triangles are going to be similar, right? So then this angle would be like angle C, right? And this smaller triangle is also going to be similar to ABC, right? Because if this is angle C, then this will be angle A, right? Because this is another right angle right here. And C, or the angle C plus the angle A have to add up to 90 degrees, right? From the ABC right triangle. And just like we have here, because C is here, A will have to be here, right? Because they add up to 90 and this whole angle is 180 and we have a right angle right there, right? So then this smaller triangle is also similar to the bigger triangle, and by the same thing, this other triangle is also similar to the bigger triangle, right? So all of these triangles are going to be similar to the big triangle. And if you're more experienced, you can pretty much see that just right away. So yeah. All right. So if we know that this smaller triangle is similar to the larger triangle, then we could do some things, right? We know that this smaller triangle is 9 over 289 of the area of the larger triangle, right? And that's a two-dimensional scaling, right? So we can just convert that into a one-dimensional scaling because the triangle is similar. So that means the triangle's side lengths will be 3 over 17. Will be 3/17 of the larger triangle's side lengths, right? So yeah, we just square rooted the two-dimensional scaling to get our one-dimensional scaling. And we could see that works fairly nicely here because 9 over 289 is or 9 and 289 are both perfect squares. So then we have a decent fraction to work with. All right. So then what we can do is we aren't given any lengths here, right? So we can assume some side length to be something, and then we work all the other sides out of that. So we can just set AB to be 1, and then so we directly get our first we could directly use our scaling of the smaller triangle to get what that side is, right? That's 3 over 17. And this is also a square, right? So we can have 3/17 here. Yeah, okay. And then from here, there's not really there's not much to apply. Like we have to start using variables. So we can call this side x maybe. That small side x. So yeah, we can do that. Okay. So then we can use our similar triangle properties, right? So we know that the ratio on the smaller triangle of this side to this side has to be the ratio of the bigger triangle from this side to this side, right? That's saying 3 over 17x has to equal 1 over BC, right? So then BC will just equal 17x over 3. So this has to be 17x over 3. And this is also 3/17 plus x, right? So then this small side would be 17x thirds minus 3/17 minus x. Oh, and you can actually you can just take 3/3 x out of that. So then you had 14x over 3 minus 3/17 right there. And this also has to be 3/17 plus x, right? All right. So then with this side, and this side, we can use the triangle similarity again, right? We know that from the small triangle, the ratio has to equal 3 over 17x, right? So then we know that 3 over 17x has to equal 3/17. Yeah, okay. 3/17 plus x over 14x thirds minus 3/17, right? And then we can see if we can find our value of x from this. If we were solving this by hand, that would be pretty bad. But luckily we have a calculator, so we can just plug this into our TI. Let me do that real quick. All right. When I plug that in, I get I do get some solutions for x. I get x equals negative root 85 minus 11 over 34. And x equals root 85 plus 11 over 34. And then we can check again, or actually 11 is going to be greater than the square root of 85, right? Because 11 is the square root of 121. Whoops. Oh, sorry. So this value here will actually be positive, right? Because root 85 minus 11 is negative, and this will make it positive again. So why do we have two positive values of x here actually? Well, in our figure, this smaller square, we can actually put it in two different spots. We can put it here, but we can also put it there. And that would make, I mean, those two cases are both perfectly fine, and they're different as well. So basically, our two different values of x are for both of those two cases. So yeah. It doesn't specify which case it is, so we could really use any one here. All right, so we want the yeah, okay, so why that doesn't matter is because we want the area of the larger square. We want the ratio of the area of the larger square to the area of the triangle, right? And we could put the smaller square in two different spots, but the larger squares are going to change, right? So that's why we have two values of x, and we can use either of them to solve for our answer. Okay, so then what is our answer going to be? Well, it's going to be our side length of the bigger square, which is 3/17 plus x squared, over the area of the triangle. And that's just going to be 1/2 times 1 times 17x over 3. All right. So we can just plug that into our TI again. Bill, how do you do the variable setting thing?
It's menu 1 1.
Can you just say like A or something?
What? Yeah, you just say a. You just say something equals, and then type in what it equals
Okay.
to. So yeah,
I'll
this is
I'll
T
try
using
both.
a calculator. So
Yeah.
calculator is a very, very useful tool.
I'll try both values of x just to make sure that both of them work. So yeah.
Right.
Oh, whoops. All right. Okay. Oh wait, hold on. All right. So I just plugged in both this value of x and this value of x into this equation, and with them were equal to 6/17. So we can see that does work out. Both x's work, and we get a common fraction. And if we look at the answers, that is the correct answer, 6/17. So I don't know. This problem, I guess it's moderately hard. Um, really, you have to like I don't know, use the two-dimensional scaling to one-dimensional scaling. That's really nice. Um, and then see that those are similar triangles, and after that, it's pretty simple. The algebra is kind of bad-ish, but I don't know. It's not that bad. Um, there are probably also a lot of other different ways to solve this. Maybe doing it with the actual area ratios, but I think just go ahead and putting it into the one-dimensional ratio would be a little bit better. Anything you want to say there, Bill?
Right. Definitely like on the 2D to 1D scaling part, and this is just taking advantage of the abilities of a calculator, basically. Um, right. I mean, besides that, this is. I mean, the overall gist of like how you would actually do this problem, it's fairly straightforward. It's just the calculations.
All right. Okay, so that was all of the team. So now we've made it through all of 2016 nationals.
So
So
are
there
we
you
going
go.
to begin 2015 nationals?
Sorry, what was that again?
So now we're going to begin 2015 nationals, right?
Yeah. Now we'll do 2015. I have it pulled up here already. So we're just gonna go ahead and start with sprint. All right. What is the slope of the line that passes through the point 6, 9, and -1, -5? Okay, pretty easy. Just really simple algebra 1. negative 5 over negative 5 minus 9 over negative 1 minus 6. So that's just, 14 over 7, which is 2. Yep, there it is. Okay, when all that is written in the form a to the r times b to the s, what is the value of r plus s? So basically, we just need to apply a lot of exponential rules to get to simplify it into that. So it should also be pretty easy as long as you know algebra 1, right? Or this is algebra 1 material, right, Bill?
Yes. Yeah.
All right. Okay. So R is just going to be actually, what we could just do, maybe to like save a little bit of time, is just to add all of these exponents and subtract all of these exponents, right? Because like R is just going to be those two minus these two, right? And S is going to be those two minus those two. And we want to find R plus S, right? So we can just add up all those and minus all those. So then our 2's cancel, our 4's cancel, our 3's cancel. We have 8 minus 1, which is 7. Yep, it's 7. Okay. What integer value of n makes the equation 1 plus 3 to the n plus 3 to the 2n equals 757 true? Um, the way I see of doing this is to set like x equal to 3 to the n, and then we have a quadratic equation in x, right? Because 3 to the 2n is also just 3 to the n squared, right? So yeah, we could solve it like this, and then we just need to solve for x, and then do that, yeah. So then this is just x squared plus x minus 756 equals 0. Not the best quadratic equation, but we will try to do it. So we should look at the prime factorization of 756 and see if we can get anything to do this. So like we're gonna have to get two factors of 756 that have a difference of 1, right? Okay. All right. So that's our prime factorization. Um, you can look at this a bit, try to figure it out. But it is just 9 times 3 and 2 times 2 times 7. So that will be 28 there, and 9 times 3 will be 27, and they differ by 1. So then we can factor that as x plus 28 times x minus 27. Those two will multiply to negative 756, and those two will add to 1. Right, so then what is x? Well, n has to be an integer. So then 3 to the n has to equal 27, right? So that n equals 3. Also, in the original equation, you can notice that you only have integer values of n, and these increase like really big as you increase n, right? So you really don't have too many cases to test. You literally just could like plug in some n values into here to see which get you 757, and maybe that's better actually. Maybe that's a little bit faster than this way. But yeah, like if you put in 5 already, like 3 to the 10 is already like ginormous, right? That's like I don't know. That's like two yeah, that's like 240 something 240 something squared. So yeah, that's really big. So like really you only have to test like 2, 3, and 4, and then yeah, I don't know. Uh what do you think, Bill? Or anything you want to say?
I mean, all the problems so far have all been really easy. So
Okay,
they're all
yeah.
like just basic algebra stuff. So
Yeah, that wasn't too bad.
there's nothing really to say about it.
Okay. What is the unit digit of 3 to the 2015? So we're gonna have to use like we're gonna
Mod
use
10.
yeah, mod 10. We're gonna look at a mod 10. And we're gonna look for periods of it, right? So so we can start with, I don't know, 3 to the first. So 3 to the first mod 10 is just going to be 3. 3 squared mod 10 is just going to be 9. 3 cubed mod 10 is just going to be 7, and 4 mod 10 is just going to be 1, right? And then we can already see we have a repeating pattern here, right? If we multiply 3 to here, we're going to get 3, and then this is going to repeat itself, right? If we multiply it by 3 again, we're going to have 9, 7, and 1, right? So then we can see we already found our repeating mod sequence. So then we can relate it, or because it's period 4, we can relate it to the mod 4 of the powers of 3, right? We could say that it's 3 mod 10 when the power is 1 mod 4, right? So then we just have to look at this power mod 4. So so what? We know 2016 is a divisor of 4, right? Because 16 divides by 4. So then 2015 is 3 mod 4. So then we look at this case and it's just 7 mod 10. So it's going to be 7. Yep. Two similar right triangles have areas of 30 centimeters squared and 270 centimeters squared. The length of the hypotenuse of the smaller triangle is 13 centimeters. What is the length of the hypotenuse of the larger triangle? So we have two-dimensional scaling and one-dimensional scaling. So, we can just convert the two-dimensional scaling to one-dimensional scaling. So our two-dimensional scaling is that the larger triangle has 9 times the area, right? And we just need to square root this to get the one-dimensional scaling. So the larger triangle is going to have 3 times the dimensions of the smaller triangle, right? So the hypotenuse of the smaller triangle is 13 centimeters, and the hypotenuse of the larger triangle is going to be 3 times 13, or 39. Yep, it's 39. The lengths of two sides of an isosceles triangle are 41 feet and 18 feet. What is the area of the triangle? Okay, so we're just given that two sides are 41 and 18. We don't know which one is the base, right? But let's see, if we have the base as 41, and then we have the sides as, or the legs as 18, this doesn't work, right? Because 18 plus 18 is not greater than 41, and it has to be greater than 41 for it to be a possible triangle, right? Like if we try to build this, we would just have like these 18 sides wouldn't be long enough to connect, right? So that's pretty simple. Then we can only have a base of 18. That means our sides have to be 41. So we just want to figure out the area of this. So this will be 9, and we have a right triangle here, and this is just 9, 40, 41 right triangle, right? So then we just do we just do 9 times 40. So that's just 360. And that's your answer. For the first 30 miles of Raphael's trip, he traveled at an average speed of 45 miles per hour. For the remaining 20 miles of that trip, he traveled at an average speed of 30 miles per hour. What was Raphael's average speed for the entire trip? Okay, so we know the total distance is what? 30 miles plus 20 miles, right? So our total distance is 50 miles. So then if we get the total time, our average speed is just going to be the total distance over the total time, right? So we just need to figure out what the total time is. And we're given the speeds in each of those trips, right? So we could just multiply those speeds by, we could divide those speeds by the distance to get the times on those trips. And then we add those times on that trips, and then we get the total time. Okay, so the time for our first trip is going to be 30 miles over 45 miles per hour, which is just what? 2/3 hours. And then for our second part, we're going to have 20 miles over 30 miles per hour, which is also 2/3 hours. So then we have our total time to be 4/3 hours. So then our speed is going to be 3/4 hours or sorry, 3/4, and the hours is going to be on the denominator times 50 miles. And we want our answer to the nearest tenth, and we can see that this doesn't fully simplify, right? So we're gonna have 75 miles over 2 hours. We just want it to the nearest tenth. So it's gonna be 32.5 miles per hour. This is a pretty simple problem. Oh, whoops. Actually, I messed up there. This should be 37. Yeah. All right, if A sharp B equals A minus 1 over B, what is the least positive integer A for which A sharp 3 also is a positive integer? Okay, we should just try plugging this A sharp 3 into there. So A sharp 3, by looking at that, is going to be equal to A minus 1 over 3, right? And then we're going to sharp this again with 3, right? Or we're going to sharp this again with 3, right? So then that would be A minus 1 over 3 minus 1 over 3, right? So then this minus 1 is just minus 3 over 3. So then we have A minus 4 over 9, getting that 3 to the bottom. And we want to find the least positive integer A for which this is also a positive integer. So for this to be a positive integer, A minus 4 has to be a divisor of 9 and greater than 9, right? Or so A is just going to be 13, right? So that is 9. So that will be the least positive integer. So A is also the least positive integer. So A has to be 13.
For this problem, another way you could do this is that you set A minus 1 over 3 minus 1 over 3 to 0 mod 3. And so that you get to A minus 1 is congruent to 3, wait, yeah, 3 mod, wait, sorry, let me do this. Yeah, so A minus 1 is congruent to 0 mod 3. And so A is congruent to, well, sorry, A minus 1 is congruent to 0 mod 3, so A is congruent to 1 mod 3. And then the least positive integer is 13. Well, it wouldn't be least. Well, yeah, so this is a better way.
Oh yeah, so uh so it's good to think of the mod stuff, but it doesn't really work here because I don't know, you don't know how that is going to lead to like the least positive integer. It's better to just expand it all the way, and then it's pretty obvious at the end.
Wait, how did you get from that A minus 1 over 3 minus 1 over 3 to A
Oh,
minus
okay.
4 over 9?
Yeah, I can
Oh,
show you.
okay, never mind.
Oh,
I
okay, yeah. So yeah, you just get this minus 1 on top, so then it would be A minus 4 over 3, and then you have, and then I'll just write it out. And then you have A minus 4 over 3 for 3, right? So you have something over something, and then it's over something. You can just multiply the overs, right? So then it's A
yeah.
minus 4 over 9. Yeah. All right. Anything you want to say, Bill?
I mean, there still isn't really much to say about this. This still ends up being a. You're just plugging the number in. It's just recursive, so there's
All
not
right.
really anything to say about it.
A frustum is created by slicing a cone parallel to its base. Two circular bases of the frustum have radii of 8 inches and 12 inches, and the height of the frustum is 4 inches as shown. What was the height of the original cone? Okay, so let me draw a rough picture here. Yeah, not the best picture. Okay. And then we should look at what our original cone would look like. So have this, right? And we can just call this X for now. Okay, so one thing to notice is that this triangle with the X and 8 is similar to the triangle with the X plus 4 and the 12, right? Why is that so? Well, we know that these two lines are parallel, right? Because the frustum, or the cone is sliced parallel, right? Parallel to the base. So those two lines have to be parallel. So that means this angle has to equal this angle. And we know that both of these are right angles, right? Because they're both heights. So then we have that these two triangles are similar by a similarity. So then we can set up a ratio, x over 8 equals x plus 4 over 12. So then we can solve for x like this. Just cross multiply. And we get 4x equals 32, or x equals 8. Alright, so we know x equals 8, then the height of the entire original cone will just be 8 plus 4, or 12. Yep, the answer is 12. The median of an arithmetic sequence of 8 integers is 44. If the first term is 30, what is the value of the 8th term? Okay, so this is like on one property of arithmetic sequences. So if you have the median or mean of the arithmetic sequence, so median or mean, that's a weird or. Then the opposite integers of the arithmetic sequence also has to have an average of this median or mean. So what I mean, get it? Okay, sorry. So like, let's say you had let's say you had 6 integers, right? So, oh no, let's just call them, I don't know, let's just call them A, B, C, D, E, F, okay. So we have 6 integers, and let's say our mean or median was x, right? Because for an arithmetic sequence, the mean or median is the same, right? So then every pair of opposite integers in F, B and E, and C and D have to average to x. And this is pretty easy to see because like let's say the common difference between all of them was like, I don't know, y. So then we could say, so x is going to be at the middle of all of this, right? So x is going to be 1/2 y from C and 1/2 y from D, right? So this is pretty easy to see that their average is x, and as we go farther, we're just adding more y's, right? So B is 3.5 y from x, and so is E, so their average is also going to be x. All right, so what is this saying? If we have the median or mean of a arithmetic sequence, then the opposite integers are going to have an average of that same number. And that's exactly what we have here. We have our median or mean is 44. We have our first term is 30, and we want to find the 8th term. And those are opposite terms, right? Because it's the first and the last term. So if we set the 8th term to be x, then their average has to be 44, and then we just solve for x. So x is going to be 58. And yeah, that's what we have. The hypotenuse of isosceles right triangle ABC is the side of square ACDE as shown. If AB is 4 units, what is the length of segment BE? Express your answer in simplest radical form. I can quickly draw the figure. So you have ABC. This is an isosceles right triangle. And AB is 4 units, so it's going to be like that. And then we have a square here. And then we want to find the length of BE. So, you know, Pythagorean theorem or 45/45 or whatever to get that this is 4 root 2. And this is a square, right? So all this is 4 root 2. And then you could get the side length in multiple ways. It's not too bad. So one way you could do it, this way is pretty straightforward, is that you know that this angle is a right angle and this angle is 45 degrees. So then this angle A, has to be 135 degrees. So then you can apply the law of cosines, right? What is the law of cosines? Quick recap. If we have any triangle, A, B, C, and we know that the angle between A and B, let's call it angle C, then the law of cosines tells us that A squared plus B squared, or sorry, C squared equals A squared plus B squared minus 2AB cosine C. So we can apply that here because you want to find what C is, which is this, and we have the side lengths AB and we have the angle C. So yeah, we could do that. Another slightly harder to find, but a little bit of faster way is to drop this side down. Whoops. Is to drop the diagonal of the square. So on the diagonal of the square, this is going to be 45 degrees, right? So this is going to be this is 45 degrees as well. So then we have a right angle there. So then we have a right triangle there, right? And the diagonal of this square is just going to be 4 root 2 times root 2, which is just 8. So then we have 8 here, we have 4 here, then just Pythagorean theorem. We just have 16 plus 64 rooted. We could go ahead and take out a 16. So then we have 4 times root of 1 plus 4. And that's just 4 root 5. And you should also get this when doing the law of cosines. Yeah, there might also be other ways. You could also do chord bash if you really wanted to, but I mean, these ways are faster. But yeah, this should be a fairly simple geometry problem. Yeah, we have 4 root 5. A triangle with one vertex at 1, 0 is graphed in the first quadrant so that one side of the triangle is on the x-axis and another side is on the y-axis. If the area of the triangle is 3 units squared, what is the slope of the third side? Okay, so we're graphing on the first quadrant. We have a vertex of 1, 0. And then one side of the triangle is on the x-axis and another is on the y-axis. So like maybe it looks like this and this, right? So that one side is on the x-axis and one side is on the y-axis, right? But obviously this doesn't work, right? This doesn't work because we have 4 points here and that's not a triangle. So the only way that this works is if these 2 points coincide at 0, 0, right? We have to have these lines meeting at 0, 0. So then we only have 3 points and they form 2 lines that are on the x-axis and the y-axis. So then we have a triangle like that. And we know that this point is at 1, 0, so this side has to be 1. Okay, and then we know that the area of the triangle is 3 units squared, right? So 1/2 times this equals 3, right? Which means that this has to be 6, right? All right, and then it's pretty easy to see that the slope is just -6, right? Because we go 1 unit right, we go 6 units down. Yep, that's our answer. What is the area of the region between the inscribed and circumscribed circles of the equilateral triangle with side length 12 units? Express your answer in terms of pi. Right? So basically we have a equilateral triangle here, it's 12 units. We have an inscribed and circumscribed circle, and we want to find the area of the region between the circles. So the best way to do this is to find the in radius and the circumradius and use that to find the areas of the circles and subtract them to get the middle area, the middle region. So there are formulas for the inscribed radii and the circumscribed radii of a triangle, and they're pretty important to know. So I'll talk about them here. So one property of the in radius, I'll call it small r, is that it times the semiperimeter. I'll label it S. So the semiperimeter is just the perimeter half of the perimeter. So you might be asking, like, why do we even use the semiperimeter? Like, why don't we just use perimeter over 2? Well, I don't know. It's just with triangles, perimeter over 2 comes up like a lot in triangle formulas. So I don't know. Mathematicians just have made a new term called semiperimeter, and that's just the perimeter over 2. So yeah. Okay. So the in radius of any triangle, doesn't have to be equilateral or right or whatever, times the semiperimeter of the triangle is going to be equal to the area of the triangle. Okay, so yeah, you could use that to find the in radius of a triangle. With circumradius, you have that the circumradius is equal to the sides of the triangles multiplied together, ABC, A times B times C, over 4 times the area. Like that. There's also another one with the circumradius. It's with the law of sines, kind of. It's that 2r will equal a over sine of the angle A. So sine of the angle opposite to this side. And these two sides and angles could be any set of sides and angles. So this is more with law of sine stuff, and if you know angles. And this stuff is more for if you just know the sides. And the area, you could also put it in just a formula of the sides, right? With Heron's formula. Heron's formula is that A will equal the semi-perimeter times the semi-perimeter minus x, times semi-perimeter minus, or why did I say x? Let's just have it as ABC. Semi-perimeter minus B times the semi-perimeter minus C. Yep. And then so we could put that into here, right? Or here. So then all these formulas for the inradius and the circumradius are just formulas of the sides, right? Which means what? Which means if you just have all the sides of any triangle, just the lengths of the sides and nothing else, then you can figure out its inradius and circumradius, which is pretty cool. And yeah, you could also find its area. All right. So yeah, we can apply this to this question. We see that our sides are 12, 12, and 12, which means that our semi-perimeter is going to be 36 over 2, or just 18. So then we can put it into all of our formulas. Let's find the area first. So the area is going to be 18 times, or the square root of 18 times 6 times 6 times 6, right? So we can get out a 6 here. We can get out another 6 here. So we're going to get 36 root just 3 left there, right? So we got 2 6s out of there, 2 6s out of there. So then just have 3. So our area is 36 times root 3. Oh, and you don't have to use this formula here, right? It's the equilateral triangle. You could figure out the area in other ways as well. So yeah, okay. And then the inradius is then just 36 root 3 over 18. So then it's 2 root 3. The circumradius will be 12 cubed over 4 times 36 over 3, or over root 3. So we can take out a 12 from 36 to take out 112 from here. And we also have 4 and 3 here, which is another 12, so we can take out another 12. So then this is 12 over root 3. We can rationalize this. So then that will just be 4 times root 3. Oh, why did I circle that? I don't know. Okay. So then we have the inradius 2 root 3 and the circumradius 4 root 3. Then we just need to square them, subtract, and multiply by pi. 4 root 3 squared is just going to be 16 times 3, which is 48, minus 4 times 3, which is 12, times pi, which is 36 pi. All right. Yeah, that's the answer. Well, a little bit long for number 13. But also, oh yeah, do you want to say something?
I mean, it's just an equilateral triangle. You don't have to do it this way.
Yeah, okay. I was about to say that.
Okay, yeah. It's equilateral
Okay.
triangle, so okay, you can.
So yeah, okay. Because we have an equilateral triangle here, everything is really nice. So you don't have to know these formulas. You could just find the inradius and circumradius geometrically because the equilateral triangle is so nice. So yeah, you could do it like that. Sure. So we know that the inradius has to be on the angle bisectors of the in center has to be on the angle bisectors of the triangle, right? So basically we can form a triangle here. Yeah, sure. Okay. So we know that this is 30, this is 60, right? So then we know that this side is 6, so then this total side has to be what? 6 times root 3? Actually, see, that's not the best way to do it, is it? Yeah, okay. Yeah, no, okay. A better way to do it is like this. Okay. So we can connect this like that, right? And if we connect it like that, then it has to be this has to be 30 degrees, right? Because this has to be an angle bisector. Yeah. So then this is 6. If we just drop this down, and this is the in radius, and this will just be oh, okay, yeah, we have a 30, 60, 90 triangle here, which means that we can just say like this is 2r, or we could say this is 6 over 2, or sorry, 6 over root 3 times 2, whichever one. Let's just say it's 2r. So then we can use Pythagorean theorem. So then 36 plus r squared equals 4r squared. So then 3r squared equals 36. And then r squared equals 12. And then r will equal 2 root 3. Right, so that's the same thing that we got before. Okay, sure. Okay. Okay, so we can also make a line here. This has to be the circumradius, right? And for an equilateral triangle, the circumcenters and the incenters are the same point. So the circumcircle and the incircle for an equilateral triangle are concentric, which means that this line, because it crosses through the in radius as well, will also be an angle bisector. So this angle will also be 30 degrees, right? So so basically this is also r, right? 2 small r is also big R. So what? We said r was 2 root 3, so then that's just saying big R is 4 root 3. Yeah. Okay, so maybe that's also nice to know that the circumradius of an equilateral triangle is exactly double its circumradius, or sorry, its in radius, yeah. So yeah, you could do it like this if you wanted to, but I don't know. Yeah, you could do it both ways, sure. Anything else you want to say, Bill?
You can also know that the circumradius is twice the in radius because, the center there, the point where the circumradius and the in radius come from is also the centroid because it's the equilateral triangle. It's the centroid. And the points, because the equilateral triangle, the lines are all the same. So the median the centroid will split the median 1 to 2. So you can also view it that way.
Sure. Yeah. All right. All right, let's move on. Jane's drawer contains 6 white socks, 4 black socks, and 2 red socks. Jane reaches into the drawer without looking and randomly selects 2 socks. What is the probability that the 2 socks she selects are the same color? Express your answer as common fraction. This is not too hard. We can just do casework. First, she gets 2 white socks, 2 black socks, and 2 red socks. And then we just add all of these probabilities together to find the probability that she gets 2 socks of the same color. So we have 12 total socks, which means that the probability that she gets 2 white socks will just be 6 over 12 times 5 over 11, right? We assume that she is doing it without replacement, right? Like, like you choose a sock, but you don't put it back in, right? Like you keep the sock. Okay, we assume that she's doing it without replacement. Okay, this will just be 4 12s times 3 11s, 2 12s times 1 11. So if you don't know this, this is just this is just the number of socks that fulfills it, right? That we can get 6 white socks over the total number of socks. And once we pick one out, we're going to have one less of that color sock that we still need, and we're also going to have one less of the total socks, okay? So all of these denominators are going to be the same, just not 121, sorry. It's going to be 132. And so we can just add the numerators together. So that's going to be 30, that's going to be 12, so 42, that's going to be 2, so 44. All right, and then what? We could take out a 2 from both of them. We can take out a 22 from both of them. Then we just get 1/3. Yep, that's our answer. Pretty simple. This one was a lot faster than the last one. So, all right. Number 15, a regular octagon has a perimeter of 96 meters. Its area in square meters can be expressed in simplest radical form as a plus b root 3. Sorry, what is the value of a plus b plus c? All right, so what we should do here is just go ahead and get its side length. Because we have a regular octagon, all of its sides are going to be the same, and we know the perimeter, right? So then the side is just going to be 96 over 8, which is just 12 meters. But we don't care about units, right? So yeah, that doesn't even have units. Why does this even have units? I don't know. Oh, it's area in square meters. Okay, whatever. I don't know. Okay, whatever. Okay, so we have an octagon. Oh yeah, I have the shape drawing. I have the polygon drawing feature. It's so good. See, we just do that. Maybe make it 100 pixels. And then boom. That's a bit small actually. Oh. Yeah, let's make it way bigger. Let's make it 500. Yes. There we go. Alright. So the sides are 12 meters, right? Okay. We can find the area in multiple ways. It's not too hard. One way we can do it is divide the octagon into sections. So we could put it like this. Okay. So then all of these would be 12, right? Just like taking that 12 everywhere, and that's also 12, right? So yeah, then we have a square of 12 here, and then this is 12, right? And this is going to be a 45-45 triangle, or right triangle, just by symmetry, and that this is a right angle, right, from these sides being perpendicular. So then this is just going to be 12 over root 2, right? So then we can find the area of these triangles and the areas of these boxes, and we know the area of the square, so we could do it like that. We could also do it in another way that I think is a little bit faster and better. So we could also use the fact that the area of a regular polygon is going to be its apothem. It's going to be 1/2 its apothem times its perimeter. So what is the apothem? Well, it's the length from the center of the polygon to any one of the sides, not the vertices, the side. That's the apothem. And this formula is pretty easy to prove just by connecting all the apothems down, right? So then you can form triangles on each of these. And each of these triangles has area 1/2 apothem times its sides, right? So when you add all of them together, you're gonna get its perimeter and still have that 1/2 times its apothem. Alright, so what? So we can just find the apothem and we have the perimeter, so then we can find the area like that. So okay, so we know that the side is what? It's 12. So just need to find the apothem. So we can connect it like that by symmetry. It's gonna put this angle into half. Or it's gonna bisect this angle. Yeah. And we can find the angle of an octagon using the sum of the sum of interior angles formula, or you can also memorize it. It's just 135 degrees. Oh, actually, it's not. This is not too good here, actually, right? I mean, unless you want to find the trig of 67.5 degrees, right? Yeah, finding the aphthem isn't too good here, right, Bill?
Uh, wait, are you trying to find the
Oh, well,
apthem this
okay,
way?
actually,
The apthem can be
actually, yeah,
found
okay,
without finding
yeah,
using
it can be
triangle.
found in different ways. Yeah, you don't have to do it like this.
Yes.
Yeah, so like again, we can divide the figure into like this, and then we can find the aphthem by drawing it here, right? So then we could do it like that. So this would just be half of this, right? That's 6. And we said that this was 12 over root 2, so that's just 12 over root 2. Yeah. So that's better than finding the trig of that. And also that's cool though, right? Because we find the aphthem here, and we also have this sideline. So basically we just now we know what the trig of 67.5 degrees is, which is pretty cool, I guess. Okay. So the aphthem is going to be 6 plus 12 root 2, and the perimeter is 96, so then the area will just be 1/2 of this. So it's going to be 48 times 6 plus 12 over root 2. 12 over root 2 is just 6 times root 2 times 48. So it can be expressed like that, and we just need to find the value of a plus b plus c, right? That's just going to be 6 plus 2 times. Oh, actually no. That's going to be 6 plus 6 times 48 plus 2. There we go. Okay, so 48 times 12. That's just going to be 480 plus 96, which is just 576. Then plus 2 is 578. And yeah, that's your answer. For what three-digit positive integer do all of the following conditions hold? The hundredth digit is 1 less than 3 times the units digit. The 10th digit is twice the units digit. The absolute difference between the integer itself and the number obtained by reversing its digits is 495. Okay, so what we can do is say the numbers A, B, C. Then we can set up some formulas. We can say that the hundredth digit is 3 times C minus 1. And B is going to be 2 times C. And the absolute difference between the integer and the reversal will be 100A plus 10B plus C minus 100C minus 10B minus A equals 0. And yeah, these cancel. 99A minus 99C equals 0. And we just have A minus C equals 0. So then we can use this and this to find that negative 2C equals negative 1. Oh, what? Wait, what? Um,
Why'd you set it to 0?
oh yeah, why did I set it to 0? That's the problem. It's equal to 495, right?
Yes.
Okay, so then this is 5. Okay, so then we have C plus 5 equals 3C minus 1. Negative 2C equals negative 6. C equals 3. Alright, and then B equals 6 and A equals C plus 5. So 8, right? So then that's E63. Yeah. Yep, we have 863. if 1101100 in base 2 squared is x cubed, what is the value of x expressed in the base 3? Okay, so what we should do here is we should convert this base 2 number into base 10, because then we can actually do arithmetic on it. And then find x and then convert it back into base 3. Or not back, just convert it into base 3. Alright, if we have 100 or 1101100 in base 2, then this in base 10 will just be 2 cubed. So that's 2 cubed, right? Because this is 0, this is 1, this is 2. So this is the third spot, this will be 2 cubed. So this is 2 to the 4th, this is 2 to the 7th, or sorry, 6th, and this is 2 to the 7th. So we just need to add these together. Hold on, sorry. Alright. So, yeah. So we can just find what this is. Or maybe to make it a little bit simpler is to factor out a 2 cubed from all of them. And then we find the sum. Okay. And then this is just 3 plus 8, which is 11, plus 16, which is 27. And this is 2 cubed. So we're going to square this and we're going to cube root it. So let's cube root that inside first. This is 3 cubed, so we're going to have 2 times 3, and this is going to be squared. So this is 36, right? So this is x. So now we just need to convert 36 into base 3. All right, so 36 in base 3. I'll just go over how to convert stuff into how to convert base 10 into other bases. So other bases, you have place values, right? So let's say you have a base of b. So these place values correspond to b to the 0, b to the first, b to the second, b to the third, right? That's what I did with that. I multiplied each of them by what place value they were on, and then I added together to find their value, right? So like if you think of the base in base 10, we have 1, 10, 100, right? So like if we say 361, we're really meaning the value of 300 plus 60 plus 1, right? So yeah, that's what bases are, right? So if you want to convert something in base 10 to a different base, you want to divide it by powers of this base to see like you're basically getting this number apart into just the sum of the factors of the base. So you want to divide this number by the largest factor of the base that you can get it to be divided by, right? So the best one to use here would be 27, right? Because that's 3 cubed. So this is just going to be 1, right? So that means on the 3 cubed spot, if b equals 3 now, we can put a 1 in the in the b cubed spot. And then yeah, because 36 divided by 27 will be 1 with some remainder, right? And this remainder, we will distribute it to these numbers, right? So what is the remainder? The remainder is 9. Well, 9 is just a power of 3, right? So it's just going to fit into the 1 of b squared. So then these are just going to be 0. Yeah, so that's 36 is just 1, 1, 0, 0 in base 3. That's your answer. If a and b are positive integers such that 1 plus 1 over a times 1 plus 1 over b equals 3 halves, and a is less than b, what is the sum of all possible values of a? Okay, so keeping it like this doesn't really do much for us. Why? Because this is just bad, right? Our information that a and b are positive integers doesn't help at all here. We would rather have some kind of expression that is multiplying with like just I don't know, just with A and B on top at least. And then if it was added to other integers, that would be better, right? Because then we could say like that's also an integer or something, and then maybe we can apply some stuff there. So we don't want to keep it like this because this really doesn't tell us anything, right? Because like this problem, if A and B are any real numbers, it's gonna have infinite solutions, right? The really crucial part in here is that A and B are only positive integers. And so there are going to be a limited number of solutions in here for A and B. So A and B are positive integers. That's a crucial part. So we have to utilize that somehow. If we keep it in this format, I mean, it's really hard to use it, right? Like 1 over a positive integer, that's just really hard to use. You want to try to like I don't know, just convert it into something better, right? Okay, so let's do that. So the simplest thing to think of is just to expand it, right? So we're gonna have 1 plus 1 over A plus 1 over B plus 1 over AB equals 3 halves. And then we can sum this fraction here. That's going to be AB plus A plus B plus 1 over AB equals 3 halves. Now, one way you could do it is you can factor this top into A plus 1 times B plus 1 over AB equals 3 halves. And then you kind of utilize the A and B are positive integers. You could say A plus 1 or B plus 1 has to be 0 mod 3. Because one of them has to be divisible by 3 for there to be a 3 on top, and likewise for A and B. We can say A and B. A or B has to be 0 mod 2, right? One of them has to be divisible by 2 so that there can be a 2 on the bottom here. But this format actually isn't too good because we have mods here, right? We're saying either these is something mod something, but that's not too good, right? Because we still have like a lot of integers to process through, right? And then we have to find some pattern to say where we can stop, right? So I don't know. If you got to this point on the test, you might just want to go ahead and utilize this, as to not waste too much time trying to look for better methods. But I don't know. There is a better method, and I don't know. Um, hmm. Maybe if on the test you wanted to look for a better method, you can. If you notice that I don't know, this isn't too good. I don't know. What do you think, Bill? Like, if you got to this point on the test, what do you think you should do?
Um, I mean, at that point, you could just try numbers. Just try some numbers and see what happens. Um, I would also, I mean, I would personally do what I did when we were going over, which is do the factoring thing. But if you got to A plus 1, B plus 1 over AB equals 3 halves, oh, at this point, I would just like try some numbers and see what happens, basically. Like, just try some numbers, like, make an attempt to get to 3 halves and see what you get.
Yeah. Yeah, you could try with this, but there's a better thing. So how you can get to that is if you cross multiply this fraction here. So then you'll have 2ab plus 2a plus 2b plus 2 equals 3ab. So then you have negative ab plus 2a plus 2b plus 2 equals 0. And then what you could do here is you can multiply it by negative 1. everywhere, just to get the AB being positive. And then you can, then this just factors into, or like you can have A minus 2 times B minus 2, right? So this will mirror this, except at the end it has a plus 4, right? So then we need to just minus 6 of this. And then we can say A minus 2 times B minus 2 equals 6. So why is this better than this? Well, this, again, we have much, right? And that's not the best. Like, A or B is congruent to 0 mod 2. That helps a little bit. But we still have a lot of things to analyze, right? Like infinite stuff to analyze. But, like, we have to find a pattern. But this is a lot better, right? Because A minus 2 and B minus 2 both have to be integers, right? Yeah, they both had to be integers. And so they had to be, and they had to multiply to 6, right? And the only factors of 6 is 6 and 1, or 1 and 6, and 3 and 2, or 2 and 3, right? So we just do it like that, right? And we also know A is less than B, so then it's just with those two cases, right? So then we just have two cases, and this is really easy to solve, right? Also for this, you might you should also briefly consider the negative. Like if these two can both be negative and they multiply to each other to equal 6, but it doesn't work here because A and B both have to be positive integers, so the least they can be is 1 and 1, which would be -1 and -1, which is too small, right? But you should consider that if I don't know, I don't know, like if these are minusing larger numbers like -4 and -3 or something, then you have to be careful. Then there will be negative solutions on there. All right. So yeah, if we just do this, then we have two cases where A minus 2 is 1 and B minus 2 is 6, and yeah. So then we could just solve for A. A will be 3 in that case, and A will be 5 in that case. Yep. And then so our sum of possible values A is just 8. Oh, wait, what? Oh, what? Oh, okay. I just said 2 plus 2 is 5. Nice. Okay. Okay, 2 plus 2 is 4. So A is 4 here. So it's not 8, it's 7. Right? Yeah, so the answer is 7. Alright. Okay, it's 8:25. Let's make this our last problem here. We have tetrahedron ABCD has side lengths AB equals AC equals 15 centimeters, BC equals 18 centimeters. Okay, and we basically just have a list of the lengths of the sides. So let me draw the tetrahedron first, and then I'll fill in the sides. So I'll just draw a generic one for now, and then maybe we could, I don't know. I'll just draw a generic one for now. Okay, so we have A. Actually, this is kind of small. I'll make it bigger. Okay, A, B, and C. AB equals AC. They're both 15. BC is 18. AD is, let me label that D. AD is 8. And BD equals BC equals 17. Okay? And we want to find the volume of the tetrahedron of ABCD. So, one thing to notice here, okay, so the first thing that you should recognize is that to find the volume of the tetrahedron, what you're gonna want to do is find the area of a base and multiply it by the height, right? So like we could try to find the area of BDC and then multiply it by the height of this A drop down, right? And we can find the area of BCD pretty easily because this is just a I mean you have the side links, right? You could use Heron's formula, but this is also a isosceles triangle, so you could do it even faster. But the problem is the height is not very good. We don't really know where it lands, and really we just can't do anything with it because all we know are the sides of the tetrahedron. So we want to find something special here. And the special thing is that this triangle, ADB, is a right triangle. 8, 15, 17 is a Pythagorean triple. So then we can say, sure, I'll label it here. Then we can say, oh, my bad. Then we can say that this angle right here is a right angle, right? Because 17 is the hypotenuse. All right. This is a little bit hard to see in the figure. Maybe I'll draw. Yeah, sure. I'll draw a new one. So this one, I'll have BDA in the back right here. So this will be A, this will be D. So this is 15, this 17, and this is B. So we have a right triangle right here, and then we have C somewhere. Sure, I'll try like here. CD is 17. AC is 15. Wait, AC is 15 as well.
Yes, AC is
AB.
15.
Oh, wait, we have two right triangles?
Is that so?
Huh.
It
Oh,
would
wow.
it would seem so that we have
Oh, wow, we actually have
two.
two right triangles.
Wait, no. No. Wait, yes we did. We did. Yes.
Yeah, we do.
Whoa.
Wow, this is crazy. Okay. Um, yeah. So this is a right triangle as well. Whoops. Whoops. This is a right triangle. And if we have this here, this is a right triangle as well. Um, and then this is kind of hard to draw now. But this right here is going to be 18. This 17 and 15. Wow. Amazing. All right. So, oh, okay. So if we look at this is it's kind of okay. Okay. Let me try to reorient this. Okay, so that it's like yeah. Okay, let me try to reorient this so that BAC is like on the ground. Okay, so imagine that this tetrahedron is on the ground here. Okay, and BAC is right here. And this is 15, 15, 18. Okay, and this is BAC, and then we have D here. Okay, and then these goes like that, and then these are right angles. There we go. That's the figure I needed. Okay, so now in this figure, you can see that this this line of B, this side, is perpendicular to the plane of ABC. Why? Because we know that it forms a right angle with the line AC from this right triangle. So then it must be perpendicular to the entire plane. So why is this so good? Well, it's because then BA is just the height of this bottom triangle right here. So then that's really easy, right? Because we have all the side lengths. So then we already know this height. So that's what we needed here. We needed to find a right triangle. And then we could use this height, height being one of the sides of the tetrahedron. And we didn't need two right angles, but I guess there just was. We only needed one right angle, but yeah. Okay, so BA is 15. And these are 15, 15, 18. So then we just need to find the area of this triangle and multiply by this height, and then by 1/3 because it's like a pyramid, right? Okay, so this is isosceles triangle, so we can drop the angle bisector of A down, then we'll have 9. And this is just 3, 4, 5 scaled up by 3, so this will be 12. So then the area of our triangle will be 1/2 times 12 times 18. And then to find the volume, we just multiply this by 15 and then by 1/3. So then this will be 2 times 18 times 15. So then this is 36 times 15. And we can just multiply this out. And then we get 0.45540. Uh-oh. Oh no. Oh no. I messed up somewhere. Oh, these are 17, right? No. Wait. Oh, this is D. Oh.
Did you misread it?
Yeah, I misread my handwriting. I thought this was B. Yeah. Okay, so this is not 15. This should be 8. Alright, then it's 36 times 8. Spicy. Then it's just 48 plus 24. Yay, then we got 288. Alright, there we go. That was our last question. We're at 8:34. So that's gonna be all for today. Thanks for watching. And yeah, we'll continue from here next time. And see you then.